Hello, this is Dr. Strickland. In this video, we will investigate the reactions of aldehydes and ketones with sulfur nucleophiles, and then we'll talk about the oxidation of aldehydes and ketones with a peroxy acid. Take a minute to look at these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. So we've talked about aldehydes and ketones reacting with a variety of nucleophiles. We talked about carbon nucleophiles, hydrogen nucleophiles, nitrogen nucleophiles, and oxygen nucleophiles. So the sulfur nucleophiles will finish this up. And an aldehyde or ketone can be transformed into a thioacetal using excess thiol and an acid catalyst. A thioacetal looks just like a regular acetal with sulfur atoms in place of the oxygen atoms. One thing about thioacetals is that you can reduce them. So I have two general reaction patterns here. This is the formation of the thioacetal, and you can see it looks just like an acetal with sulfurs in place of the oxygens. You could hydrolyze it off and get right back to the aldehyde or ketone that you started with, just using water and an acid catalyst. But the other thing you can do with thioacetals is catalytic hydrogenation with hydrogen gas and rainy nickel, and take the sulfurs off completely without putting back the carbon-oxygen double bond. And this turns out to be useful in some synthesis problems. So the first thing we're going to do here is a roadmap. So I want you to complete the roadmap by adding the missing reagents over the arrows. So remember, with any roadmap, the first thing you want to do is find out the compound that's kind of the center of everything. So that's this guy here. And we can turn this by way of a thioacetal into this, or by way of a regular acetal into that, or we can reduce the ketone. So what I want you to do is tell me what the reagents would be in those two places, and then come on back. Okay, welcome back. So I bet what you have here is 1,2-ethane diol and some sort of an acid catalyst. I'm just going to put hydrochloric acid here. To make the thioacetal, we just need the corresponding dithiol. Now, I want you to tell me about these three, and I want you to name the three final products. All right, so pause the video and do those things, and then come on back. Okay, welcome back. So if you want to totally remove the thioacetal, this is the catalytic hydrogenation. And rainy nickel is just a specialized catalyst for catalytic hydrogenation. If you want to go back to the carbonyl that you came from, this is just acid catalyzed hydrolysis of an acetal. And if you want to reduce the ketone to the secondary alcohol, there are several different reducing agents you could use. I think I'm going to go with the weakest one that I can think of. And I'm going to use ethanol in the second step as to protonate. Okay, so what are the names of these things? Well, if we've just got the two methyl groups on here, then we're going to have to start numbering at one of them. Four, five. Totally did that wrong. 1, 2, 3, 4, 5, 6. There we go. So this is 1,3-dimethyl cyclohexane. And then this guy here, we have to be mindful of the group of highest priority. And so that's the OH group, the hydroxyl group of the alcohol. So, and you can either go clockwise or counterclockwise. So this is 2,6-dimethyl cyclohexanol. And we've got a similar situation over here with the ketone, where this has to be carbon 1. And I'm going to continue numbering clockwise, but counterclockwise would be fine. 2,6-dimethyl. Going to run out of space, so I'm going to put the rest of it down here. Cyclohexanone. Okay. So that's the story on sulfur nucleophiles and what you can do with them. So let's take a look at what's called the Baeyer-Villiger oxidation. And the Baeyer-Villiger oxidation is known as a crossover reaction because it can be used to convert a ketone or aldehyde, which will undergo acyl addition, into a carboxylic acid derivative, which undergoes acyl substitution. So aldehydes and ketones are significantly different in their reactions from the carboxylic acid derivatives. And so this is a big deal to be able to go from one of these sets to the other. Now, the thing that we have here is actually the conjugate base of a peroxy acid. And this guy is called peroxy trifluoroacetate, or the peroxy trifluoro, run out of room here, acetate ion. And this is what's used to take an aldehyde and turn it into a carboxylic acid, or a ketone and turn it into an ester. And this is the only oxidation of a ketone that I know of, and it's certainly the only one we've talked about in our class. Now, look down here before we talk about relative migration tendencies. Look down here. If you've got this ketone, the question is, which side gets the extra oxygen? Because it's not always to the right of the carbonyl. It can go maybe over here or maybe over there. And that does have to do with relative migration tendencies. And what we've found experimentally is that a hydrogen will move more easily than anything else. After that, a tertiary alkyl group has the greatest tendency to migrate. Then a secondary alkyl group, which is about the same as a phenyl group, that is a benzene ring that's a substituent. And then primary alkyl groups, and then bringing up the rear is just a methyl group. Okay, so in that case, let's see what we've got to the left and to the right of this carbonyl. We've got this on one side and this on another side. So let's look at what it would be where it's attached to the carbonyl carbon. Clearly to the right here, this is just a methyl group. And over here, since it's connected to a secondary carbon, this is a secondary alkyl connection. So the one that's more likely to migrate is this one. And because of that, the methyl group stays where it is, but the oxygen is going to get inserted right there. And so it makes this ester. It makes the cyclohexyl ester instead of the methyl ester. All right, come on over here to this one. Take a look at what's to the left of the carbonyl and what's to the right of the carbonyl. Decide which one is more likely to migrate and draw me the product. And then come on back. Okay, welcome back. So from our relative migration tendencies, you know that the hydrogen is more likely to migrate. And this is one of those things you just have to memorize. So we know that the phenyl side is going to stay where it is because it's less likely to migrate than the hydrogen. And so it turns this aldehyde into a carboxylic acid. All right, let's take a look at the mechanism, and we're going to do the aldehyde into the carboxylic acid. Here's my aldehyde. And then trifluoromethyl group right there to the left of the carbonyl. The peroxy part is the oxygen-oxygen single bond. And then oxygen-oxygen single bond is a very weak bond, very easily broken. The oxygen on the end is the nucleophilic atom, and it attacks the carbonyl carbon. All right, so that brings us to here, and the negative charge goes to this oxygen. The hydrogen is still there. And then here is the rest of our peroxy trifluoroacetate. Get our electrons in there. And then this is the migration. When the carbon-oxygen double bond is reformed, the group either to the left or the right of this carbon that will migrate more easily does so. In this case, it's the hydrogen. And then that breaks the oxygen-oxygen single bond. Okay, so when we unfold this, let's see what changed and what didn't. There's the carbon-oxygen double bond. And then if you want, you can just do it like this to just see where everything went. The bond between the carbon and the oxygen is still intact. It's the bond between the carbon and the hydrogen that moved. And then we've got then this anion. All right. Okay. So please answer the question at the end of this video and then come on back.